Welcome back, everyone. You know, our last deep dive, the one about the .NET garbage collector, really got me thinking
Yeah.
about how we can write, really efficient C# code. Like, how can we squeeze out every ounce of performance? So today, we're diving even deeper
Oh, nice.
into this whole world of structs and how knowing where they live in memory heap versus stack, can really make a difference. And get this, we're going to bust a myth. A real internet myth, the kind that spreads like wildfire.
Okay, lay it on me.
That structs always live on the stack. Not always true.
Ooh, yeah, that's a good one. Lots of folks get tripped up by that.
Definitely. But before we get all myth busting, let's start with the basics. What exactly are structs? I mean, I know they hold data and all, but how are they different from classes, in the grand scheme of things?
Well, at their heart, structs are what we call value types. And this little distinction, it's super important when you start thinking about memory. When you create a struct and then assign it to a new variable, you're making an entirely new copy. Like the whole shebang.
So like a photocopy, not just a link to the original.
Exactly. You got it. Now, classes, on the other hand, those are reference types. Assign a class to new variable. All you're copying is a reference, like a pointer to the original. Think of it as sharing a link, maybe to a Google Doc.
So with classes, multiple variables could be pointing to the same thing, which means if you change it through one, all the others see that change. But with structs, each one's its own island.
Exactly. Now, this difference in how they handle copies, it ties directly into where they hang out in memory. And to really get that, we need to talk about the two main memory areas, the heap and the stack.
The heap and the stack sounds like a buddy cop movie, right?
It does. All right, so think of the heap like a big, bustling city, constantly changing. Objects are allocated there as you need them. And it's managed by, you guessed it, the garbage collector. Keeps things tidy. Now the stack, that's more like a neatly organized stack of plates. Last one in is the first one out. Super efficient for handling like local variables and those quick function calls.
Okay, so heaps the busy city, stacks the well-organized library. Got it.
Perfect. And here's where we tackle that myth. We often think of structs as hanging out on the stack, and usually that's true, but they can actually end up on the heap too.
Wait, what? But I thought, the internet says structs always live on the stack.
See, that's the trap. Let's say you've got a struct, a date time, tucked inside a class. Now classes, those reference types, they live on the heap. So any struct hanging out in there, it goes on the heap too. Its lifetime's connected to that owning object.
So it's not just about being a struct, but where you fit into the bigger picture.
You nailed it. And another example is, think about closures. Closures can capture variables from their surroundings, right? If a closure snags a struct, that struct might need to outlive its original scope. And guess where it ends up? The heap. Gotta stay accessible.
Mind blown. All right, the structs always on the stack myth officially debunked. But honestly, why should we, as developers, care about where this stuff lives? Does it really impact our code?
Oh, absolutely. Big time. This whole memory thing, it has a huge impact on performance. Especially when you consider the garbage collector. The more stuff we put on the heap, the harder it has to work. And that can mean, pauses in our applications.
Right, those moments where everything freezes up. Definitely not a good look for users.
No, not at all. Now, there's this process called boxing where you convert a value type, like our struct friend, into an object, which is a reference type. This forces the struct onto the heap, even if it normally be on the stack.
So even if it's happy on the stack, boxing's like, nope, heap time.
Exactly. And this whole boxing and unboxing thing, it adds extra work, slows things down, especially when you're constantly creating and destroying objects.
Yeah.
Which brings us to a crucial point. When to use structs versus classes? Gotta choose the right tool for the job.
Oh, okay. Decision time. So when should we reach for a struct, and when's a class the better choice? Give us the rundown.
Structs are your go-to for, small data-focused things. Minimal behavior, just holding information. Coordinates, colors, simple data structures, that kind of stuff.
And what about classes?
Classes are the heavy lifters. For bigger, more complex objects, lots of functionality, methods. If you need things like inheritance or polymorphism, classes are your friend.
Got it. Structs for small, efficient data chunks. Classes for the big stuff with lots of behavior. But, C# is always evolving. What about those newer features that play into this whole memory management game?
Oh yeah, C# keeps getting better. And it keeps giving us more control over structs and how they behave. Like, for example, readily struct. It's this key word that says, hey, the struct, immutable, no changes allowed.
So the depiler's like the bouncer saying, nope, no modifications here.
Exactly. And since the compiler knows it can't change, it can do some clever optimizations, potentially boosting performance. Pretty neat, huh?
Yeah, that's cool.
Huh?
Are there other C# features that give us this kind of fine-grained control?
You bet. There's this powerful one called struct. It guarantees a struct stays on the stack, no heap allowed whatsoever. Like a backstage pass straight to the stack, no waiting in line.
Struct, the ultimate performance booster. But sounds pretty restrictive if it can't go to the heap at all.
It is. Struct is for specific scenarios, those where performance is paramount. You gotta avoid the heap completely. Think about the SPANT type. Have you heard of that one?
SPANT. Oh yeah, that mysterious force everyone's talking about in the performance world.
Yeah, it's a perfect example of how struct can be incredibly powerful. SPANT lets you work directly with memory, like right in the thick of it. No copying, no allocation overhead. Imagine you've got this window into an array accessing data without creating new copies.
So it's like a ninja silently moving through memory, leaving no trace.
That's a great way to put it. The performance benefits are amazing, especially when you're dealing with strings or large arrays.
Incredible. It sounds like SPANT can be a real game changer. But wait, you said SPANT is a struct, so it lives on the stack. Doesn't that kind of limit it? What if I need to store data for a long time? Or, like, pass it across asynchronous boundaries?
Yeah, you're right. Being stuck on the stack means SPANT has its limitations. If you need to store things long-term, or pass data between functions that aren't on the same stack frame, or do asynchronous stuff, then SPANT isn't the best choice. Gotta stick with more traditional approaches in those cases.
So it's like a specialized tool, super powerful, but for specific tasks. Are there any other techniques we can use to keep that garbage collector happy, especially when we're dealing with, like, lots of temporary data?
Absolutely. There's another tool in our high-performance kit, and it's called Stack-a-lock.
Stack-a-lock. The name kind of gives it away. Sounds like it allocates stuff on the stack.
You got it. It lets you grab memory directly on the stack. No heap involved. Think of it like reserving a private study room in that well-organized library of ours. No need to check out books from the busy city.
I love how our analogies are coming together.
Yeah.
So with Stack-a-lock, we get a direct line to the stack. But when would you actually use this in your code, like in real life?
Imagine you're working with, say, an image processing algorithm. You need a temporary buffer to store some pixel data while you're crunching numbers. Putting that buffer on the heap could trigger the garbage collector, especially if you're processing loads of images.
Right, especially if that image processing happens all the time, like in a game or something.
Exactly. But with Stack-a-lock, you can just grab that buffer right on the stack. Boom, no garbage collection overhead. Potentially makes your code a lot faster.
That's impressive. It's like a secret weapon for when you just need a quick workspace.
It can be. But like any powerful tool, Stack-a-lock comes with caveats. The memory you get, it's only valid within that function. Once you leave the function, it's gone. Poof.
So not for storing things long-term, just for quick operations where you need a temporary space.
Exactly. It's all about using the right tool at the right time. Think of SPANT as your way to access and manipulate existing memory without creating copies. And then Stack-a-lock is for those quick temporary buffers right on the stack.
I'm seeing a pattern here. High-performance C# code, it's all about knowing where your data lives, heap versus stack, and using the right tools to keep things running smoothly. And of course, keeping the garbage collector happy.
You got it. It's not just about writing clever algorithms, it's about making smart choices every step of the way. From the data structures you use to how you manage that memory.
This has been eye-opening. I feel like I'm starting to see, like, the matrix behind my code. All those ones and zeros flying around.
I like that. Understanding what's going on under the hood opens up a whole new world.
It definitely does. But before we go full Neo, are there any other techniques we haven't covered yet that can help us keep that garbage collector in check? We've talked about SPANT, Stack-a-lock. What else is in our high-performance toolbox?
Well, there are always more tools, right? High-performance coding, it's a deep rabbit hole. But yeah, there are definitely some other tricks we can pull out of our sleeves.
Okay, I'm ready to go deeper. Hit me with your best performance wisdom.
All right, let's talk about something called object pooling. It's a technique for, think of it like recycling, but for objects in your code.
Object pooling. Recycling objects. I'm intrigued. Tell me more.
So picture this. You've got this type of object that's super expensive to create. Maybe it involves a ton of calculations or network calls or whatever. Now, instead of constantly creating and destroying these objects, what if we could, reuse them?
Okay, so we're not throwing them away each time. We're keeping them around, ready to be used again.
Exactly. We create a pool of these objects up front. When you need one, you borrow it from the pool, use it, then return it when you're done.
Kind of like a library for objects. I like it.
Precisely. And this has some serious benefits, especially when it comes to performance.
Like what? Give me the good stuff.
Well, first off, it can massively reduce the workload on the garbage collector. Fewer objects being created and destroyed, fewer GC cycles, shorter pauses. It can make your application run way smoother, especially if you're creating objects frequently.
So smoother performance, less garbage collection overhead. That's a win-win. But are there any downsides to using object pooling?
There are some trade-offs, yeah. Mainly, it adds a bit of complexity. You got to manage the pool itself, make sure objects are returned properly, handle any potential threading issues if you've got multiple threads accessing the pool, so it's not a magic bullet for every situation.
Got it. Powerful tool, but got to use it strategically.
Exactly. And you also got to think about the state of the objects in the pool. If they have any internal data that needs to be reset before they're reused, you need to handle that. Otherwise, you might get some weird behavior.
Right. Don't want to accidentally reuse an object that's in the wrong state. Okay, so we've talked data structures, object pooling. Are there any other general guidelines for minimizing the impact of the garbage collector, even if we're not using these advanced techniques?
Absolutely. Even without diving into object pooling or spanpate, there are some simple but incredibly effective practices that can make a huge difference in how your code interacts with the garbage collector.
Okay, I'm all ears. Lay it on me.
Remember those generations we talked about in that first deep dive? Generation 0, Generation 1, Generation 2. It's like sorting laundry.
Yes, that was a brilliant analogy. It made understanding the garbage collector so much easier.
One key principle is to try to keep object lifespans short whenever possible. If you can keep those temporary objects in Generation 0, the garbage collector can clean them up quickly and efficiently.
It's like keeping our coding workspace tidy, so the cleanup crew has an easier job.
Precisely. Another helpful tip is to use value types strategically. Remember, value types like structs are stored directly in memory, often leading to fewer allocations and less pressure on the garbage collector compared to reference types.
So even the choice of data type can impact garbage collection. It's all connected.
Exactly. And finally, a simple but often overlooked principle. Avoid unnecessary object creation. Reuse objects whenever possible, and be mindful of operations that create a lot of temporary objects, especially within loops.
It's the coding equivalent of reduce, reuse, recycle.
Exactly. These simple practices go a long way in making your code garbage collector friendly, leading to smoother and more performant applications.
This has been so insightful. We've gone from demystifying the garbage collector to object pooling, and now we're talking about strategic object creation and even laundry analogies. I feel like I'm starting to see the matrix behind my code. But before we go down that rabbit hole, I have a feeling we're just scratching the surface of high-performance coding. There's got to be more, right?
You're absolutely right. While those general guidelines are a fantastic starting point, there are even more specialized techniques for those who want to go deeper into the world of performance optimization. And that's precisely where we're headed next. All right, so we've covered a lot of ground. We talked about structs, where they live in memory, how to use them effectively. We even dipped our toes into object pooling.
Right. Feels like we've really leveled up our performance game. But I have a hunch you've got more tricks up your sleeve.
Oh, you know me too well. There's one more area I wanted to touch on. It's a bit more advanced, maybe even a little dangerous if you're not careful.
Ooh, now you've got me really curious. What is this dangerous territory?
We're going to talk about unmanaged memory, the wild west of memory management.
Unmanaged memory. That sounds kind of intimidating, like stepping outside the safe, cozy world of .NET where the garbage collector takes care of everything.
Yeah, it's definitely stepping outside the comfort zone, but for certain situations, it can unlock some serious performance gains.
Okay, I'm listening. But first, remind me, what exactly is unmanaged memory?
So remember how we've been talking about the garbage collector, how it keeps track of objects, cleans up the ones we're not using, makes sure we don't accidentally mess up memory? Well, unmanaged memory is like going off the grid. We're responsible for everything ourselves.
So no garbage collector safety net. We're on our own.
That's right. We decide where to allocate memory, how much to use, and when to free it up. It's all on us.
Sounds powerful, but also kind of scary. Why would we even want to do that when the garbage collector is so good at, well, collecting garbage?
There are times when it makes sense. Like if you're dealing with external libraries, maybe something written in C or C++E, or if you need to interact directly with hardware.
Ah, so bridging the gap between the .NET world and the unmanaged world.
Exactly. And these external components, they often work with pointers and raw memory addresses. That's where unmanaged code comes in.
Okay, I'm starting to get it.
Mm.
But how do we actually do that in C#? Doesn't the language try to prevent us from doing these kinds of low-level memory manipulations?
It does, usually. But C# recognizes that sometimes you need to get your hands dirty. And that's where the unsafe keyword comes in.
Unsafe. That doesn't sound promising.
It's basically a warning sign, right? It's like saying, hey, compiler, I know this looks sketchy, but trust me, I've got this.
So it's like getting a special permit to do something risky. You acknowledge the dangers, but you're willing to take the chance.
Exactly. But just like with any risky activity, you got to be careful, know what you're doing.
All right, lay it on me. What are the risks of working with unmanaged memory? What could go wrong if we're not careful?
The biggest danger is accidentally accessing memory that you shouldn't. If you've got a pointer pointing to the wrong place and you try to read or write there, well, bad things can happen. Crashes, corrupted data, even security vulnerabilities.
Yikes. Okay, that's definitely something to avoid.
Another common pitfall is memory leaks. Remember, we're in charge of freeing up memory now. If we forget, that memory stays occupied even if we're not using it anymore.
So it's like hoarding old stuff, never throwing anything away. Eventually you run out of space.
That's a great way to put it. And these memory leaks, they can add up over time, causing your application to slow down, use more and more memory, and eventually crash.
Okay, unmanaged memory, powerful, but definitely a double-edged sword. So let's say we've thought about the risks, and we still think unmanaged memory is the way to go. Any tips for working with it safely? Like, how do we survive in this wild west of memory management?
First rule. Always, always, always free the memory you allocate. Use marshal.allocHglobal to get the memory and marshal freeHglobal to release it when you're done. And make sure you free it in the same scope where you allocated it to avoid those nasty memory leaks.
Allocate, use, free.
Got it.
Got it. Anything else?
Be super careful with pointer arithmetic. You can do things like add or subtract from pointers, but if you mess up, you could end up accessing memory that's off limits, leading to all sorts of trouble.
Right. Better to be safe than sorry. Any other words of wisdom?
Try to keep your unsafe code as small and contained as possible. Like put it in separate helper functions or classes. That way the risky stuff is isolated and it's easier to see what's going on.
Okay, I'm taking note. Minimize unsafe blocks, encapsulate the risky code. It sounds like we need to approach unmanaged memory with a lot of respect.
You got it. It's a powerful tool, but not something to be taken lightly.
This deep dive has been amazing. I feel like I've learned so much, not just about structs and memory management, but about the whole performance landscape in C#.
It's been fun, right? Remember, high-performance coding, it's a journey. The .NET world is always evolving, so stay curious, keep experimenting, and always be on the lookout for new ways to optimize your code.
Absolutely. A huge thanks to our expert for guiding us through this complex world. And to our listeners, thanks for joining us on this epic deep dive. We'll see you next time for another exciting exploration of the world of .NET. Until then, happy coding.